Welcome to G Fun Facts Online. Today, we're diving deep into one of the world's busiest bodies of water, the North Sea. But we're not looking at the ships or the oil rigs on its surface. We're going beneath the waves to a hidden world that's constantly in motion. Imagine a desert, but underwater. Now, imagine that desert is sculpted into colossal sand dunes, some as tall as a 5-story building and stretching for nearly a kilometer. These aren't static hills of sand. They are living, breathing, moving giants, known as sand waves. They are some of the largest and most active on our planet, and they shape everything in their path, from tiny marine creatures to billion-dollar energy projects. This is the story of the North Sea's sunken giants, how they're born, the life they support, and the immense challenges they pose to our modern world. Let's start with their staggering scale. For centuries, sailors and fishermen had hints of this strange underwater topography. They called them ridges or humps that would unexpectedly snag their fishing nets and depth-measuring lines. But it wasn't until the 1930s, with the invention of echo-sounding technology, that we got our first real glimpse. A Dutch engineer named John van Veen was a pioneer, creating the first graphical profiles of what he called submarine sand dunes. His charts revealed wave-like structures that continued for miles, some reaching heights of 13 meters or over 40 feet. Fast forward to today, and our technology has painted a much clearer picture. Using multi-beam echo sounders, which sweep the seafloor with a fan of sound beams, scientists can now create high-resolution 3D maps, and what they've found is stunning. These sandwave fields cover vast areas of the North Sea floor. The distance from one crest to the next, what scientists call the wavelength, can be anywhere from 100 to 1,000 meters. Their height is just as impressive. In a channel that's 40 meters deep, it's possible to find a sand wave that is 20 meters high. That's a truly massive structure that completely changes the local seascape. And these giants are on the move. Driven by the relentless push and pull of the tides, they migrate across the seabed. In most areas, this movement is slow, maybe a few meters per year. But in places with stronger currents, that rate can jump to tens of meters annually. In fact, studies in wind farm areas have recorded some features moving up to 155 meters in just 5 years. To add another layer of complexity, these giant sand waves often have smaller dunes, called megaripples, riding on their backs. And those megaripples can have even smaller ripples on them. It's a complex, multi-layered system, all moving and evolving at different speeds, governed by the immense power of the sea. So how does the ocean build something so enormous? The creation of these sand waves is a fascinating process that scientists call spontaneous bedform generation. It all begins with the North Sea's powerful tides. For a sand wave to form, the current needs to be strong enough to lift sand particles off the seabed. Once that happens, any tiny irregularity on the seafloor, a small bump or a dip, can kickstart the whole process. As the tide flows over this initial bump, the water flow is slightly disturbed. This creates a very faint, tidally averaged vertical movement in the water, which in turn generates a flow near the seafloor that moves sand from the low points or troughs towards the high points or crests. If this upward push of sand is stronger than the downward pull of gravity, more sand gets deposited on the crest than is removed. The bump starts to grow. As it gets bigger, it disturbs the water flow even more, which makes the upward flow of sand even stronger, which makes the bump grow even bigger. It's a self-reinforcing feedback loop that can turn a tiny imperfection into a towering sand wave. The final shape of the sand wave depends on the tides. If the incoming and outgoing tides are perfectly balanced, the sand wave will be symmetrical and stay in one place. But that's rare. In most of the North Sea, the tides are asymmetrical. One direction is stronger or lasts longer than the other. This imbalance means more sand gets pushed up one side of the sand wave. Grains of sand are carried up the gentler slope and then cascade down the steeper side, causing the entire sand wave to slowly migrate in the direction of the dominant current. This gives it a classic asymmetric profile, a gentle upstream slope and a steep downstream face. While tides are the architects, storms are the powerful modifiers. A major storm can generate waves and currents strong enough to stir up huge amounts of sediment from the seafloor. This intense energy often has a flattening effect, reducing the height of the sand waves. At the same time, the powerful storm-driven currents can dramatically speed up their migration or even reverse it temporarily. One study estimated that the effect of a single major storm on sand wave movement could be equivalent to 20 years of normal, calm weather. It's this constant dance between the slow, steady construction by tides and the occasional, violent reshaping by storms that defines the life of these underwater giants. Now, you might think that a constantly shifting desert of sand would be a terrible place to live, but these sand wave fields are the complete opposite of barren wastelands. They are complex, three-dimensional habitats that act as biodiversity hotspots on the otherwise flat, sandy plains of the North Sea floor. The key is the variety of microhabitats they create. The conditions on a sand wave's crest, where currents are strongest, are completely different from the conditions in the sheltered trough. This allows a huge range of species to find their own perfect niche. The animals here can be split into two groups. First is the infauna, the creatures that live buried inside the sand. This includes countless species of worms tunneling through the sediment, and various types of shellfish, like cockles, that bury themselves and extend siphons up to the water to feed. Some of these worms are what we call ecosystem engineers. The sand mason worm, for example, builds a tube for itself out of sand grains and mucus. When thousands of these worms build their tubes together, they can form small reefs that stabilize the sand and create complex structures for other organisms to live on. The second group is the epifauna, the animals living on the surface. Crabs, shrimp, and starfish crawl across the sediment, scavenging for food. The more stable flanks of the sand waves often host sea anemones and sponges, which anchor themselves to any available stone or shell. This dynamic landscape is also critical for fish. The sandbanks and dune fields provide essential shelter and serve as breeding grounds for many species. Flatfish, like the commercially valuable sole and dab, are masters of camouflage here, using the slopes to ambush prey and hide from predators. The swirling currents over the crests also concentrate plankton, creating rich feeding grounds that attract large schools of fish like herring and mackerel. All this life at the bottom of the food chain supports larger animals. The thriving fish stocks are a vital food source for seabirds and marine mammals. Seals, porpoises, and even whales are drawn to these productive underwater landscapes to hunt. So, these colossal structures, sculpted by pure physics, become the foundation for a vibrant and complex ecosystem that ripples all the way to the surface. But this dynamic environment, so beneficial for marine life, poses a massive challenge for us. The North Sea is one of the most intensely used marine areas in the world. It's crisscrossed by major shipping lanes, a dense web of subsea infrastructure, and a rapidly growing number of offshore wind farms. For the engineers who build here, a seabed that refuses to stay still is a nightmare. Take pipelines and cables, for instance. A huge network of pipelines carries oil and gas across the North Sea floor, alongside vital telecommunication and power cables. To protect them from damage from things like ship anchors, they are buried in the sediment. But burying a cable in a sand wave field is incredibly tricky. A cable buried at what seems like a safe depth in a trough can become dangerously exposed as the sand wave migrates away, leaving the trough deeper in its wake. Conversely, a pipeline laid over a crest will eventually find itself suspended in mid-water as the crest moves on. This creates what engineers call free spans, unsupported sections of pipeline that are vulnerable to vibrations from currents, which can cause metal fatigue and, eventually, catastrophic failure. To avoid this, engineers must conduct incredibly detailed surveys and use complex models to predict how the sand waves will move over the 30 or 40-year lifespan of a pipeline. They have to calculate a design bed level, the lowest possible point the seabed will reach, to ensure the pipeline stays safely buried. The rise of offshore wind energy has added another layer of complexity. A wind farm isn't just one structure. It can be hundreds of giant turbines, each with a foundation driven deep into the seabed. Many of the largest North Sea wind farms are located in areas with significant sand wave activity. The biggest problem for a wind turbine foundation is scour. The massive structure of the turbine's base disrupts the local water flow, accelerating it and creating a vortex that digs away the sediment. This carves out a deep scour pit around the foundation, which reduces the stability of the pile and makes it more susceptible to fatigue from wind and wave loads. In a sand wave field, this natural scour is compounded by the overall movement of the seabed. To fight this, engineers typically lay a protective blanket of large rocks, called rock armor, around the base of each turbine. Designing and installing these protections for hundreds of turbines is a massive, expensive undertaking, and their long-term effectiveness on a moving seabed is still a major area of research. And of course, there's the oldest hazard of all: navigation. The crests of the largest sand waves can dramatically reduce the water depth, posing a serious threat to deep draft vessels like supertankers and massive container ships. This is especially dangerous in the busy shipping channels leading to major European ports like Rotterdam. To guarantee safe passage, authorities have to ensure a minimum water depth. This requires constant surveying and frequent dredging operations to literally shave the tops off the most hazardous sand waves. But this is a never-ending battle. Sand waves are natural features. When you dredge their crests, the very same forces that built them in the first place immediately start to build them back up again. It's a perpetual expensive fight against the relentless power of the sea. So how do we know all this? Our understanding has been built on decades of improving technology. The workhorse of modern seabed mapping is the multi-beam echo sounder, creating those detailed 3D maps I mentioned earlier. By conducting repeat surveys over months and years, scientists can track sand wave migration with incredible precision. To see beneath the surface, they use sub-bottom profilers. These send a lower frequency sound pulse that penetrates the sand, revealing the internal layers left behind as the dunes have migrated over time, giving us a geological record of their movement. Of course, direct sampling with grabbers and cores is also essential to understand the sand itself. And more recently, autonomous underwater vehicles, or AUVs, are revolutionizing the field. These robotic submarines can get closer to the seabed than any ship, providing ultra-high-resolution data. All of this information feeds into powerful computer models that simulate the physics of sand wave formation, helping us forecast their future behavior and the impact of our own activities. But perhaps the most fascinating part of the story is where the sand itself comes from. The story of the North Sea's sand waves is really the story of the last ice age. Around 20,000 years ago, global sea levels were about 120 meters lower than they are today. The southern North Sea wasn't a sea at all. It was a vast, frozen plain of tundra known as Doggerland, which connected Great Britain to mainland Europe. As the massive ice sheets covering northern Europe began to melt, colossal rivers swollen with meltwater flowed across Doggerland, dumping enormous quantities of sand and gravel. As sea levels continued to rise, the sea slowly flooded this plain, creating the shallow sea we know today. This process left behind a thick blanket of sand on the new seabed. When the modern tidal patterns of the North Sea were established, these powerful currents had an abundant supply of material to work with. They began sorting it, moving it and sculpting it into the vast sand wave fields we see today. The sunken giants of the North Sea are, in a very real sense, the ghosts of a drowned world, the reworked remnants of a lost landscape. brought to life by the unceasing energy of the tides. The colossal sand formations hidden beneath the North Sea are so much more than a geological curiosity. They are a powerful testament to the forces that shape our planet. They are a vital, dynamic part of the North Sea system, a constantly shifting world that creates unique habitats for life and poses significant challenges for us. As we continue to expand our presence in the oceans, our relationship with these moving giants will only become more important. Understanding their behavior is a practical necessity for safely and sustainably using our seas. Through science and technology, we are finally appreciating the true scale and complexity of this hidden realm, a powerful reminder that even in one of the world's busiest seas, there are still vast wild landscapes waiting to be discovered, just beneath the waves. Thanks for listening to G Fun Facts Online.